Hello everyone. So today we're going to go over section 5.3, stretching graphs of conic sections. So once again, the three types of conic sections are circles and ellipse, hyperbolas, and parabolas. So the circle or the ellipse are always closed curves. The hyperbolas have two branches and also two asymptotes, whereas a parabola will have a single branch and no asymptotes. Okay, so given that each square is 1/2 by 1/2, we can find the equations for each one of these three graphs. Actually, there are four graphs here. So the first one is simply a circle centered at 0, 0, with radius equal to 1. Just going to redraw the arrow here. Right, so the equation would simply be x squared plus y squared equal to 1. For the hyperbolic graphs, we have two of them. The first one have x-intercepts at -1, 0 and 1, 0. And its equation is x squared minus y squared equals 1. We also have a hyperbola with y-intercepts, so 0, 1, and also 0, -1. And its equation is y squared minus x squared equals 1. Or it could also be written as x squared minus y squared equal to -1. Next up, we have the parabola. So this is just the standard parabola y equals x squared. Of course, the vertex here is just 0, 0, and it is did not undergo any vertical stretch. So this point is 1, 1, and on the left we have -1, 1. And finally, we also have a parabola on its side. And the equation for this, I'm going to use a different color than the graph. This will be x equals to y squared. Okay. So in order to obtain the graphs of other conic sections, we are going to expand or compress, so stretch these basic graphs. So when we stretch a circle horizontally, we end up with some kind of an ellipse. The hyperbolas, we can also do the same thing and get other hyperbolas. And we have done vertical stretches of parabolas before. So that should be familiar. So we are going to look at this equation here. Y equals to a times f of b, and then x minus c close parenthesis plus d, which tells us that there are some transformations according to A, B, C, D, as we have seen in previous units. So what we're going to do is rearrange the expression slightly here. First, we're going to subtract d from both sides. So that's right here. And then we divide both sides by a. And finally, the third step here is that the b variable will be rewritten as divided by 1 over b, which is the same thing, just rearranged slightly. So once the equation is in this final form, we know that starting with the letter a, so here's the letter a, it tells us that the graph underwent a vertical stretch by a. Next up is the letter b, now written as 1 over b. That will give us a horizontal stretch by 1 over b. Next up, we have the letter C, right here. That is a horizontal translation by C to the right. And finally, the letter D, that is a vertical translation by D. So for today, we are going to be focusing on just the horizontal and vertical stretches. We're not going to translate the graphs just yet. So all we're doing is changing the shape of the graph, and we're going to use the functions, or sorry, not functions, the equations from above to do that. So again, in order to get some kind of a either larger circle or smaller circle or an ellipse, we will use x squared plus y squared equals 1, and then change the values of a and b there. To get a different hyperbola, we'll manipulate the equations here, and then finally to change parabolas, we'll be changing the equations x equals to y squared or y equals x squared. Okay, so let's look at our first example. We're given the equations y over 3 squared minus x over 3 squared minus y squared equals 1, and also y squared over 2 minus x squared equals 1. So notice the difference here is that the first equation, x over 3 is all squared, so the exponent's on the outside of the parentheses, and in the second equation, y squared is inside the parentheses, so that is different. So let's look at what the difference actually means. In the first equation, x over 3 all squared minus y squared equals 1, we know that the base form of this is the x squared minus y squared equal to 1, which is a hyperbola. With x-intercepts. In this case, but it is right. It is the one that has the two branches on the left and the right. Sorry about that. So it is the x squared minus y squared equals 1 hyperbola, the one that has the left-hand side and the right-hand side are the two branches, and it undergoes a horizontal stretch by a factor of 3. Okay. Now the second example we have here, notice that y squared over 2, the y squared is kind of by itself. So if we were to rewrite this, we can rewrite this as y over root 2 all squared. So this is not a vertical stretch by 2, this is a vertical stretch by square root of 2. So the second part of example 2, we have the y squared minus x squared equals 1 hyperbola. So that is the hyperbola with a top and bottom part. So just like we saw at the beginning of this section, and it undergoes a vertical stretch by root 2. Okay. Just a quick aside, if we were having something like 2y all squared minus x squared equals 1, then that would be the same hyperbola vertically stretched by 1/2. Okay, so in the next examples, we will be graphing some of these conic sections. In this first case, we have x squared over 9 minus y squared over 4 equals 1. Okay. So once again, this is the kind of the horizontal hyperbola with the left and right branches. And what we're going to do is rewrite the equation a bit first. So instead of x squared over 9, we can write it as x over 3 all squared. And likewise for the y variable, we have y over 2 all squared, and that's going to be equal to 1. Okay. So of course the idea here is the two transformations were a horizontal stretch by 3 and a vertical stretch by 2. Okay. So one of the defining characteristics of the hyperbola are its asymptotes. So let's find those for this equation here. So we're going to use what we've used before, and that is determine what happens if when the absolute value of x is large. Okay, so then we have x squared over 9 minus y squared over 4 is equal to 1. We can isolate y by itself, so that will be y squared over 4 is equal to x squared over 9 minus 1. We can now multiply both sides by 4, so we get y squared is equal to 4x squared over 9 minus 4. And the idea here is when the absolute value of x is very large, this 4 here will be almost negligible. So when the absolute value of x is large, the expression simplifies to y squared is approximately equal to 4x squared over 9. And finally, if we take the square root of both sides, we can find the asymptote. Y is approximately equal to positive or negative 2 over 3x. So these are the asymptotes. Now this is the very formal way of finding the asymptotes. There is a slightly quicker way of finding the asymptotes, which we'll go over in the example below. Okay, so let's draw in these two asymptotes. Over 3, something like this. Sorry about that. Okay, so that's 1. Oh, sorry about that. I drew that totally wrong. That didn't work at all. I'm just going to delete it and draw it again. Sorry about that. Let's see. 2 2 over 3. Right, that's right. And then 4 and 6. Right, this is more correct. Sorry about that. So that's one of the lines. And that is, of course, y equals to 2 over 3x. And the second asymptote, same thing, going the opposite direction. So it'll look like this. Okay, and this is going to be y equals to negative 2 over 3x. All right. So once we have that, again, of course, it goes through those 4 points, rise 2 and run of 3, and then the next thing we have are the x-intercepts. So simply, the x-intercepts for this hyperbola will be 3, 0, and also negative 3, 0. Let's just draw them in. And the reason we know that these are the two x-intercepts is because the graph is simply the x squared minus y squared equals 1 hyperbola horizontally stretched by 3. So the x-intercepts will also be horizontally stretched by 3. So that's how we end up with 3, 0 and negative 3, 0. After that, the rest of the graph is a matter of using the table of values to determine some additional points. Okay, so I'm going to go ahead and draw in some additional points that were found previously using a calculator and a table of values. So something like this. Okay, and then on the other side. So we're not going to formally go through the using a table of values, but these are the points that the hyperbola would go through. And finally, the last step is to draw a smooth curve through all the points. Again, we're just going to do our best here. So something like this would be a sufficient sketch of the graph. And that's it. So when it comes to graphing a hyperbola, we're looking for the transformations, so stretches and translations. For today, it's just stretches. And then afterwards, finding the asymptotes, and then using the transformations to find the vertices, in this case, they are 3, 0 and negative 3, 0. Drawing in the asymptote, and then using a table of values to find additional points. So that is the process. And also asks us to write its equation in general form as well. So simply what we can do is, starting with the equation here, we can multiply both sides by the common denominator of 36. So once we do that, the left-hand side becomes 4. I'm just going to write this in a different color, actually. Here we're going to write x squared over 9 minus y squared over 4 is equal to 1. So multiply everything by 36. Just make a note of it on the right. So this becomes 4x squared minus 9y squared is equal to 36. And so finally, we can just move the constants to the left-hand side as well. So we have 4x squared minus 9y squared minus 36 equals 0. And that will be the general form for this hyperbola. Okay. So next up we have a different equation. We actually have two equations here. In the next part we have x squared plus 4y squared equals 36. That's our first part here. And then we also have 4x squared minus y squared plus 16 equals 0. So these are, of course, written in not the form that we're used to, kind of more closer to the general form. And so we are going to rearrange these. Let's start the first one. I'm going to go ahead and write this one in blue. So the first step here is to divide both sides by 36. So instead of x squared plus 4y squared equals 36, we'll end up with x squared over 36 plus y squared over 9, and that's going to be equal to 1. So from there, we can rewrite x squared over 36 as x over 6 all squared plus y over 3 all squared, and that's going to be equal to 1. So of course, this will be an ellipse centered at 0, 0, and it is a circle that's gone through a horizontal stretch by 6 and a vertical stretch by 3. Okay. So since it was not translated, we know that its center is going to be at 0, 0. Okay, we know that the x-intercepts, there will be 2 of them, instead of being at plus and minus 1, because of the horizontal stretch by 6, the x-intercepts will be at plus or minus 6. And also the y-intercept, instead of being at, again, plus or minus 1, they will be at plus or minus 3 because of vertical stretch by 3. Okay. So now we have enough information to draw the shape. We have the center, we have the y-intercepts, both positive and negative. We also have the x-intercepts, both positive and negative as well. So of course, the center is not part of the curve. It is useful to indicate that's where it is. And also go ahead and label the points here, 0, 3, the positive y-intercept. 0, negative 3, of course, is on the graph as well. Likewise for 6, 0, and negative 6, 0. Okay. Just going to go ahead and draw that in. Something that looks like this. Much easier to draw than a hyperbola. So here we have it. And that's all we need to do. So the other piece of information as well is that there are 2 lines of symmetry for an ellipse. The one that goes through horizontally like this, and one that's vertical. Now, depending on whether it is the wider part or the narrower part of the ellipse, these 2 axes have different names. So the axis that goes through the wider part of the ellipse is called the major axis. And the line that travels through the narrow part of the ellipse is the minor axis. Okay. All right, so let's move on to the next example. We have here 4x squared minus y squared plus 16 equals 0. So I'm just going to go ahead and rearrange the terms slightly. Just going to go ahead and do this one in red. So we can rewrite this as y squared minus 4x squared is equal to 16. Okay. So we know that this is going to be a hyperbola that's vertical, which means its branches will be at the top and the bottom of the graph. So we're going to go ahead and divide both sides by 16 here. So we have y squared over 16 minus 4, x squared over 4 is equal to 1. And of course, we can rewrite y squared over 16 as y over 4 all squared. And then minus x over 2 all squared. And that's going to be equal to 1. So that's going to be the y squared minus x squared equals 1 hyperbola, and then horizontally stretched by 2 and vertically stretched by 4. Let's write that down. So horizontal stretch by 2, by 2, vertical stretch by 4. Okay, so we're looking for the asymptotes. So instead of setting at the absolute value of x to be very large and solving for the asymptotes that way, we can also just consider what transformation took place on the asymptotes, because the stretches that were applied to the graph will also be applied to the asymptotes. So instead of y equals positive or negative x, we know that this graph undergoes a horizontal stretch by 2 and a vertical stretch by 4. And in order to apply those, we'll rewrite this as 1/4 y is equal to plus or minus 1/2 x. And then we can solve for y. So y is going to be equal to plus or minus 2x, and those will be our new asymptotes. Okay, let's go ahead and draw those in. Let's use this color here. That will be something like this. So of course it goes through 1, 2, 2, 4, and 3, 6, and also on the negative side. And then for negative 2x, we can also draw in the points first to make it a little bit easier. And it will look like this. Sorry, just a little bit off there. There we go. All right, so these are our asymptotes. The line y equals 2x, and also y equals negative 2x. Okay, so the next piece is to find out where the y-intercepts are. And the y-intercepts will be at 0, 4, and 0, negative 4. And the idea here is the original y squared minus x squared equals 1 hyperbola would have had the intercepts 0 plus or minus 1, but then it undergoes a vertical stretch by 4, so we end up with the points that we have right now. Okay, we can also draw in additional points using a table of values. And if we were to use a table of values, we would have gotten points in these locations here. Something like this. 3 and 4. And finally, we're just going to draw a curve through all the points, doing the best we can. And that will be a reasonable sketch of the hyperbola that we were given. also on the other side. And that's it. So today we looked at, once again, the different conic sections. This time around we looked at how to do vertical stretches and horizontal stretches, and also look at rewriting equations in general form and how to interpret equations that were already in general form for different conic sections. And that's it for today. So once again, thank you for listening.